p of x, which is the coefficient of y, is given by this, okay, and our q of x, which is on this other side, the coefficient of y square, is given by this x cube, and then our h of x, which is the function of x standing alone, is given by this x to the power 5. All right, so in this case we have been told that y is equal to x is a solution. So if y is equal to x is a solution, to get the other solution, like I said, we're going to use the substitution y is equal to w is equal to y minus v. So in this case, v is that first solution, so we're using here to represent a solution, v of x. Okay, so in this case, because y is equal to x is a solution, that means our v, which is one of the solutions that we know is x, so that's the solution here. V is equal to x. So the next thing is we're going to say, they said this one is a solution. Okay, that means we are saying that in this case y is equal to v is a solution. All right, that's some function of x is a solution. This is a solution to the differential equation. Then we want to find the other solution, then we use this substitution, w is equal to y minus v. So we're going to have w equal to y minus v. So our v is that solution. In this case, that solution is x. So from here it will follow that y is equal to w plus x. Why are we doing this? We want to use this substitution here so that our function at the end of the day, our differential equation at the end of the day, will depend on only w and x. Then we'll solve for w, then we'll come back to put it here to get our second solution. Second solution will be y is equal to some function of x. So we're going to use this to replace y right there, and then what we use to replace the y dx. So let's get that. So we're going to have the y dx, or say y prime, to be equal to the w dx plus 1. That's going to give us this here. So when we make that substitution, wherever we add the y dx, we're going to put this in. So this is going to give us something like this. So let's just put it in the original equation. Okay, we have just done this so as to establish that it is actually a Riccati's ODE. So let's put it in the original equation. I think that is more compact. That is going to give us the y dx. So instead of this, the y dx that we have here now, we're going to put in the w dx plus 1. So this is going to be the w dx plus 1 is equal to x cube, putting in x cube. Then we have y minus x. Y minus x is our w, okay, all squared, plus y over x. Well, don't forget that y is w plus x, okay, then divided by x. So at the end of the day, we're going to have the w dx plus 1 is equal to x cube w squared plus this w over x and plus 1. Right, so what kind of equation is this? Firstly, we know this, we cancel this out. Then at the end of the day, we're going to have the w dx. Then we move this to this side, that will be minus 1 over x multiplied by w is equal to x cube w squared. So pay attention to this new equation now. This new equation is in terms of w and x, but it is now a Bernoulli equation. Why? We now have the dependent variable to be some power here. So this is now reduced to a Bernoulli equation with n equal to 2. So we will now solve it the same way we solved the Bernoulli equation earlier. Okay, so that solution, this solution now will result to our w, and then when we get our w, we will now use that to get our y, which is the second solution we are looking for. Alright, to do that, we will, as before, consider the method for solving the Bernoulli equation. So we now have a Bernoulli equation to solve. So let's solve the Bernoulli equation for the w dx minus 1 over x w is equal to x cube w squared. So from here, we will say in this case that our n is equal to 2. So we use the substitution as we did for Bernoulli equation case. So we're going to use the substitution. Don't forget we're dealing with a different v entirely here. We're going to say v is equal to y raised to power 1 minus n. So this is going to be y raised to power 1 minus 2, that's minus 1. So v is equal to 1 over y, if you like. So then in this case we're solving this equation, okay? When we're done, we'll go back to substitute it here and then continue with this solution to our Riccati's ODE. Okay, so for now, just take this as a whole or a part on its of its own. So this is going to be, so we need to reduce this now to a linear equation. So from here we know that the v dx is equal to derivative of this is going to be minus 1 y raised to power minus 2, then the y dx. So at the end of the day we're going to have the y dx to be equal to y squared then minus y squared dv dx. So it's as simple as that. Oh, we're not using y here. You know our dependent variable is not y, is w. So this should be w instead of y. W so yeah, that's that. So we're substituting this now. So instead of the w dx that we have here, we'll be replacing it with minus y squared dv dx. So we're going to have minus y squared dv dx minus 1 over x multiplied by w, just leave it that way first, is equal to x raised to power 3, sorry, y is w, so this should be w squared minus w squared. So this will be x w squared. Then divide all through by minus w squared so that you clear these coefficients. That's going to give you the v dx, okay, plus, so this will become plus when you multiply by negative, then this will be 1 over x multiplied by w, then divided by w squared. So this is going to be equal to, so dividing by w squared, we cancel this, that would be minus x to power 3. And then at the end of the day we now have this to be dv dx plus 1 over x, okay, w over w squared, that's 1 over w, so that will be 1 over x w, okay, is equal to minus x cubed, and then we'll get our integrating factor. So our integrating factor in this case is equal to, so we should get v, okay, at the end of the day, from what we have done here, 1 over w is v, okay, so we have to get v here. So this expression w over w squared, that will give us 1 over w, which is v, so we can put v in that, as we have done before. So this is just 1 over this multiplied by v, so to give us a linear equation at the end of the day. So we'll go from this Bernoulli equation to a linear equation now, which we can now solve using our usual method. So let me write this out more clearly. This is the v dx plus 1 over x. You know we are eliminating that, we are substituting v. If we want to replace w with v, so at the end of the day we're going to have an equation that doesn't carry w, so that's it, w over w squared. So whenever you're doing this, do always clear off if you have done it properly, if you have used the proper substitutions, okay? So this is going to be v is equal to minus x to the power 3. So this is now a linear equation, a linear first order equation, and we're going to get our integrating factor mu of x to be equal to e raised to power minus, sorry, e raised to power integral, there's no minus here, integral of p of x. So our p of x is this coefficient of the dependence variable. So this is going to be integral of 1 over x dx. So this is going to be e raised to power ln x, and then this is going to be equal to x. So our variable, our integrating factor is x, so we multiply the equation through by x. When we multiply this through by x, we're going to have x dv dx plus 1 over x v, okay, 1 over x v multiplied by x. So this is x multiplying this. So I'm multiplying through by x, so x is multiplying this, x is multiplying this, is equal to minus x raised to power 4. You know, I'm multiplying this by x also. So this is going to give us, as I've said before, this will always give you the x of the integrating factor x multiplied by the dependent variable v, and that's exactly what it is, minus x to the power 4. Of course, if you try to check this, when you differentiate this, differentiate v with respect to x, keeping x constant, that will be the v dx multiplied by x. Then you know this is x over x, which is 1. So when you differentiate with respect to x, that's dx over dx, that's 1 multiplied by v, keeping the v constant, to give you this. So at the end of the day, I'm going to say that the x v, okay, is equal to minus x to the power 4 dx. So I can integrate this and integrate this. So I said integral of the whatever is just whatever. So this is x v is equal to integral of the, that's minus x to the power 5 all over 5, then plus the constants of integration. So that is that. Then from here we're going to get v to be equal to, when you divide this through by x, that will be minus x to the power 4 all over 5, then plus c over x, that will be c x to minus 1. Alright, so that's our v in this case. So follow through, we used v to represent 1 over w. So from here we can get our w is going to be 1 over v. So basically, therefore, w that we really needed, that we're trying to solve for in this Bernoulli equation, is going to be given by this here, by the inverse of this. So that's going to be minus x to the power 4 over 5 plus c x to the power minus 1, then everything here raised to the power minus 1. So that's our w. So that's that for this part that was reduced to a Bernoulli equation. And don't forget, we started with a Riccati's equation where we want to get our new solution, other solution to be y equal to w plus x. So from here now, the other solution will now be, so from there we say that the other solution is given by y equal to w plus x, or omega. This could have been omega or whatever. So this is going to be giving us y is equal to w. W is minus x to the power 4 over 5 plus c x to the power minus 1 raised to the power minus 1, then plus x. So that will be our other solution. So that means the solutions to the Riccati's ODE will be the one we are given, which was y equal to x, and then this was given, then the other one which we just found now is just going to be this plus x. So, and life can be as easy as that for differential equations. Okay. Alright, so this is the solution. This is actually the correct solution. Your p of x is not this. You will have to first reduce this. Not minus 1 over x, it's actually 1 over x as we have done it here. So notice there's a slight difference between what we got here and what the lecturer did. There's an error in the lecturer's solution where he took this as the p of x and then solved directly, but that's not appropriate. This ought to be returned to a linear equation first, because this is not linear. This is Bernoulli equation as it is currently. So you go through this and get this. You can also verify this by taking the derivative and seeing that it aligns with what we have there in the original equation. So that's about the non-linear equation reducible to linear form. Then you can also have higher order differential equations that you can reduce to a lower order. So we now consider reducible higher order differential equations. So we consider just two critical cases. Number one case is if y is absent. That means y is not in the differential equation. Now usually, of course, in this case we are considering a second order differential equation. that can be reduced to a first order differential equation. So we can solve it using any of the methods of solving first order differential equations that we have considered so far. So we're just concerned with two critical cases here. If y is absent, and then if y is present, okay, if y is present and x is absent. So we're going to look at those two cases now with a problem each, so you know how to approach it. So if y is absent, you are going to use a substitution. P is equal to y prime. Y prime in this case is just the y, the x, okay. So if y is present and x is absent, we're going to use a substitution. P is equal to what is it now? We're going to use a substitution. P is equal to the p dy. So we're going to use something like that. P is going to depend on only y. That means that if y is absent, we are suggesting that the y, the x is simply a function that depends only on y. Okay, so if it's a function that depends only on y, then the derivative of it, okay, that's the derivative of the y dx, that is going to be our y prime prime, should be equal to some f prime of y. Okay, so that will help. Okay, to be very, very specific, it means that when y is absent, we're going to have y prime to be replaced with p, which is going to be some function that depends on x. And in this case, yeah, instead of f, let me use p, so that this will be p prime. And in this case, we're going to have y prime. Y prime is the same as the y dx, So y prime is going to be replaced by p, which we are suggesting will depend only on y. Okay, so that's the difference between these two. So let's solve a problem on each so that you understand what we're talking about. Look at number 6 problem. Solve for y in the equation y prime prime equal to 1. This is the y dx multiplied by the square y dx square. So this is non-linear second order differential equation. So in this case, y is not there, so we can use this first approach. Okay, look at this number 7 too. Here y is present but x is not there, so we can use this second approach. Look at the third one. Y is present also, this y, but x is not there, so we use this second approach. Then the number 8, y is there also, but x is not there, so we use this second approach. And this last one also, y is there but x is not there, so we use the second approach. So let's solve this one, and then we solve one of these, then we follow the patterns to solve the rest yourself. So look at this first one. We're given that y prime is equal to 1. That means that when you multiply, this means that when you multiply the y, the x, okay, by the square y, the x squared is actually equal to 1. This is a differential equation. Okay, so in this case what we're doing is that, okay, since y is not there, can we can reduce this thing to a first order differential equation by simply setting some function p of x to be y. That means we say that let's y prime, which is the y dx, to be equal to some function p of x. So if that is the case, when we differentiate this again, we're going to have y prime, that is the second derivative of y with respect to x, to be equal to the first derivative of p with respect to x, so to be equal to p prime, or say the p dx. And then we can substitute this into this equation. So if we want to make the substitution, that means we must have a substitution for y prime, we must have a substitution for y prime prime. So that's what we have just done here. So by setting y prime to be p of x, then we must set y prime prime to be p prime of x, derivative with respect to x. So when we put that in this equation, we're going to have y prime, which is p of x, multiplied by y prime prime, which is p prime of x, to be equal to 1. So from here, don't forget p prime of x is the p dx, so this is just p of x multiplied by, or say just p multiplied by the p dx is equal to 1. So from here we can separate the variables. We're going to have the p dx is equal to 1 over p, and then we can cross multiply. We say that, I'll say this was not necessary, we say that p the p is equal to the x. So we can integrate. So from here we're going to have our integral of p with respect to p, that's p squared over 2, integral of the x, that is x. Alright, so from here, that of course plus some constant c, so this is going to be p squared is equal to 2x plus 2c is still a constant c. So from here we're going to have our p to be equal to 2x plus c, okay, raised to power 1 over 2. So don't forget, p is not what we need to solve this differential equation. What we need to get actually is y, which is a function of x. So to get y from here, we will make this substitution back. So we know that what we have just found is y prime. So we said y prime to be equal to p of x. We found p of x. Now that means y prime is equal to this 2 of x plus c, okay, raised to power 1 over 2. Alright, so that means that our dy dx is equal to 2x plus c raised to power 1 over 2. And then from here we're going to have our dy to be equal to 2x plus c raised to power 1 over 2. And then you can integrate and integrate, this is the x. Then this is going to give us y is equal to integral of this, that will be integral of 2 raised to power x plus c raised to power 1 over 2 dx. And then we can just write out that result here. We're going to have this as before, just like you're integrating with respect to the core and multiplying by the derivative of the core. So this is going to be equal to, or something like that, divide by the derivative of the core. So if you are integrating with respect to the core, we're going to have something like this is going to be 2x plus c, okay, raised to power 1 over 2 minus 1 divided by 1 over 2 minus 1, sorry, 1 over 2 plus 1 by integrating, divided by 1 over 2 plus 1, then divide by the derivative of the core. Derivative of this is 2, so we'll multiply by 1 over 2. So that will be our answer, plus another constant. So we can call this constant k, or you could have called this one c1 and then this one c2, so it doesn't make any difference. So in this case, we're going to have our y to be equal to, I hope you understand what I'm doing here. The idea here is that if I have a function of a function, let's say that I want to integrate something like 2x plus 1, or differentiate 2x plus 1 raised to power 2, or let's say raised to power 3. If I want to differentiate this with respect to x, I will say differentiate with respect to the core, that's 3, I'll bring down the 3, then 2x plus 1, okay, raised to power 2, then we'll multiply by the derivative of the core, which is 2. So at the end of the day, it will give us 6 into 2x plus 1 raised to power 2. So if I want to integrate this, then I can use something similar, just the reverse of it. I can integrate with respect to the core. That means I'll integrate with respect to this, and then I'm going to get something like 2x plus 1 raised to power 2 plus 1 all over 2 plus 1. Okay, this 6 is still there as a constant. Then in this case, instead of multiplying by the derivative of the core, I'm going to divide by the derivative of the core, which is 2. Derivative of this is 2. So at the end of the day, this is 3. 3 times 2 is 6. It will cancel this. So at the end of the day, I'm going to get back my original result, which is 2x plus 1 raised to power 2 plus 1, which is 3. So that's the idea here that I'm making use of. I'm integrating with respect to the core. To integrate with respect to this, I'm going to have this to be whatever I have here, raised to power 1 over 2 plus 1 divided by 1 over 2 plus 1, then multiply and then divide by the derivative of the core. That will be this. And then, so at the end of the day, I'm going to have this to be raised to power 3 over 2. So this is going to be 3 over 2. This is going to be 2x plus c raised to power 3 over 2. Then divided by, this is 3 over 2 multiplied by 2, that is 3. Then plus the constant k of integration. So that is that for our solution. Okay, so you can see that we have two constants of integration. Yes, constants of integration will usually depend on the order of the differential equation you are solving. We still look at second order differential equations in details. That's the next topic after this, but then you're not required to do this for this test, so it's fine. Right, so well, usually, generally, when you're solving the second order differential equation, you want to get the general solution. You will always have two constants of integration. You may be asked to find specific solution where what we call initial value problem, but we're not doing that here. So you usually have two constants. If you're solving first order, you have only one constant of integration. If you are solving third order, for instance, that means you have three constants of integration. So that is that for this part when y is absent. So we're going to use this approach. Okay, so for when y is present but x is absent, so let's deal with a situation like that. When x is present, when y is present but x is absent, we can deal with one of them to see how it works. So let's take this next problem. So we want to solve this differential equation. We have y to power 3 y1 y prime prime is equal to 1. When we say look at it, if y is absent, it means that y is not there. It's not the same thing as saying that y prime or y prime prime is absent. So you know, this one is not y, this is the y dx, this is the square y dx square. So that's what we mean by y is absent here. So here there is y present, because you can have y alone, which is not its derivatives. Okay, you can have its power, that's still y present. So that's what we mean by that's differentiation. And yeah, making difference we've made there. All right, so in this case y is present but x is absent, so we can still reduce it to first order differential equation. Don't forget what we said. So I'm going to use this substitution: y prime is equal to p of y, unlike what we did here where y prime was p of x. So we're assuming that y prime is some function that depends only on y. So if that is the case, that means that we're saying that y prime is some function p that depends only on y. Of course, this means that dy dx is equal to p of y, and then it will follow that when we differentiate this square y the x squared. You know why we need to do that? You know, we'll be substituting this for y prime. Y prime is not here, so it's not a big deal. If it was there, that's what we'll substitute. Okay, the square y the x squared. When you want to differentiate this is a function of a function. Okay, y itself is a function of x, so this function of a function. So we first differentiate this with respect to y. That will be the p of y dy, then multiply by the derivative of y with respect to x. Okay, so basically this means that you are differentiating this, which is the same as differentiating this, and by product rule you can get this. Okay, p of y dy. So this is just going to be equal to the p of y dy, that is the same as having p prime, and then the y dx is what we have noted as p. So this is just p prime multiplied by p. So this will help us get our p, which is a function of y. All right, then so that means our, in this case now, our y prime prime is equal to this, our y prime is equal to this, of course. So we're going to make this substitution into this given equation. Then we're going to have, therefore, y cube multiplied by y prime prime, which is p prime p, is equal to 1. Okay, so at the end of the day, we're going to have this to be p prime p is equal to 1 over y to power 3. Okay, so we have the p dy. Don't forget our p prime is the p dy. So we have the p dy, okay, multiplied by p to be equal to 1 over y to power 3. So we can separate the variables. This is going to be p, the p is equal to, I hope you got what we did here. P prime is the p dy. This is where we came about p prime, which is the p dy. Okay, so that's what we've done here. The p dy multiplied by p